Welcome to The Explainer. Today we are looking at something that honestly feels straight out of a sci-fi movie. We're digging into the DBbun bio-inspired design physics document, and it reveals how engineers are quite literally extracting the biological superpowers of animals and turning them into hard aerospace math for DARPA's synthetic mission simulator. It is just this incredible bridge between biomechanics and engineering, and we're going to unpack exactly how the whole thing works.
Okay, before we get too deep in the weeds, let's just lay down a quick ground rule. We are entering a synthetic simulation universe here. So the equations we're exploring, they aren't meant to perfectly predict some real-world flight test happening tomorrow. Instead, think of these animal traits as tuning dials in a highly calibrated digital playground. It's a setup that lets experts safely crash, brake, and rank these massive heavy-lift drone designs without blowing millions of dollars in the real world.
So what does a cheetah, an albatross, and a next-generation heavy-lift drone actually have in common? Sounds like the setup to a weird joke, right? But the answer lies in literally millions of years of the most brutal research and development process ever: evolution. Nature has already solved the absolute toughest physics problems imaginable. Whether we are talking about burst power, sustained lift, insane aerodynamic efficiency, or just surviving a massive drop, engineers are waking up to the fact that the perfect blueprints have already been drawn.
Here is our flight plan for today. We'll start in the synthetic universe, look at generating massive lift, move on to cruising for efficiency, figure out mastering wind and payload, and finally, surviving the landing.
All right, part one, the synthetic universe. This is exactly where biology collides with hard aerospace math. What is incredibly cool here is this whole cast of characters. Engineers essentially get this visual menu of biological options to pick from. You've got the harpy eagle mapped straight to extreme burst power, the albatross for energy-dense gliding, and even tigers for structural landing gear. Every single animal you see was picked for a highly measurable biological trait that translates directly into vertical takeoff and landing mechanics.
But how do you actually simulate this without the software just breaking? Well, they use a math shortcut for hover power. The simulator runs on a calibration coefficient, basically a K value, set at 8.0. Now, for context, a strictly physical 12-rotor drone uses a coefficient way up at 14.2. So this lower number acts as a surrogate dial. It essentially cheats physics just enough so the simulation doesn't instantly crash when they're testing these wild experimental designs. It gives them a calibrated baseline to test crazy ideas safely.
Moving right along to phase two, generating massive lift. Because how exactly do we get these ridiculously heavy payloads off the ground using animal inspiration?
If you want to completely break the standard rules of aerodynamics, you just have to look at the humble bee. Bees exploit something called the wheeze, fog, clap, and fling mechanism. To put that in perspective, standard airplane wings give you lift coefficients of maybe 0.8 to 1.2. But the bee's rapid, unsteady wing flapping creates this intense vortex that achieves extreme lift coefficients of 1.5 to 2.0. If engineers can design drone propellers that can actually tolerate those sudden, violent bursts of air, that can massively improve heavy hovering. And the math on this is just wild. When you translate that bee's extreme lift into our standard hover power equation, it mathematically works out to an incredible 18.4% power reduction in hover mode. Now, the simulator conservatively caps this at a 12.5% reduction just to keep some safety margins when scaling up to physical drone rotors, but still, the potential of mimicking a tiny insect to lift massive payloads is absolutely incredible.
Now, think about a raptor or a cheetah exploding into a sprint. They rely on fast twitch muscle fibers for this massive 3 to 5 times burst of power right at takeoff. To engineer a physical equivalent of that, we have to lean on supercapacitors. These basically act as dedicated energy buffers so the drone's main battery voltage doesn't sag or dangerously plummet when it attempts an aggressive vertical climb. Combine that buffer with larger propellers, and that massive burst of energy actually shoves you upward instead of the blades just spinning uselessly in the air.
Okay, let's shift gears to traveling long distances with Section 3, cruising for efficiency.
This number right here instantly shows you why engineers are basically obsessed with stealing aerodynamic secrets from the albatross. A typical drone wing has a maximum lift-to-drag ratio of about 11.1, which means it glides 11 feet forward for every single foot it drops. The wandering albatross, on the other hand, hits an astonishing ratio of 35.3. By integrating those high-aspect, long, super stiff carbon fiber wings, drones can drastically slash the battery power they need over long flights.
And it's not just the shape of the wing, it's the whole strategy. Albatrosses use what's called dynamic soaring. First, they climb way up to altitude. Second, they actively plan out glide segments by just cutting their power. And third, they literally extract energy directly from wind shear gradients. In the simulation, running this tactic yields a 15% reduction in cruise power. Add in that high aspect wing we just talked about, and you are looking at over 20% in massive battery savings, literally just by riding the wind like a seabird.
Now let's contrast that soaring albatross with the crazy agility of a bat. Bat wings have over 25 controllable degrees of freedom. They are essentially highly flexible, complex joints. Translating that to a drone means engineering foldable wings and morphing materials. We're talking heavy-duty hinges and incredibly complex mid-air software to manage the rapidly shifting aerodynamics. But the payoff? You get a totally compact drone for tight hovering, plus a 10% cruise efficiency gain because the wing can physically adapt its curve or its camber once it's fully unfolded.
Which brings us to probably the most dangerous part of any heavy lift mission, Section 4, Mastering Wind and Payload. Because how do you keep this thing stable when unpredictable weather suddenly strikes?
I want you to really picture this for a second. You've got a multi-million-dollar drone. It is carrying a massive, heavy sling load directly beneath its airframe, and it is flying straight into a 30-knot headwind. What exactly happens when that heavy payload starts swinging back and forth?
So engineers actually look to the osprey to solve this. Ospreys carry fish head first right beneath their bodies, dealing with the exact same brutal pendulum dynamics. The math shows that a swinging payload creates a resonance that can dangerously overlap with the drone's own internal balancing computer. To fix it, engineers steal osprey-inspired tactics. They use passive elastomer damping, which is just a fancy way of saying rubbery shock absorbers in the mounts, and sway-limiting algorithms that act like really smart brakes, stopping the swing before it literally tears the drone right out of the sky.
To fight the wind even further, we go right back to insects. Take a look at a dragonfly. It independently controls 4 separate wings with just incredible precision. By applying this concept of distributed thrust to drones, basically adding more rotors and breaking up the power distribution, engineers create a highly fail-safe machine. In the simulator, this translates directly to a 20% drop in control failures, because if one rotor gets slammed by a massive gust of wind, the system just instantly reallocates the power to the others and stays perfectly level.
All right, final phase of the flight profile. Section 5, surviving the landing. Because getting the payload there is totally useless if the machine smashes itself to pieces when it hits the ground.
For this, engineers look to the big cats. I mean, a tiger can absorb the landing forces of a massive 6-meter jump, hitting the dirt at 11 meters per second without breaking a single bone in its body. The engineering math derived from that is just fantastic. But designing landing gear with progressive springs that perfectly mimic a tiger's muscles lengthening under tension to act as shock absorbers, just a 20% increase in landing gear weight yields a massive 50% improvement in survivable touchdown speeds.
But it's not just about beefing up the legs. It's the spine. It's the tendons. A cheetah's Achilles tendon naturally returns about 90% of its stored energy. By mimicking that with low-stretch cables wired right into the drone's frame, engineers shift those really dangerous bending forces directly into tension. Combined with a flexible spine that redistributes the stress during a hard impact, they end up saving critical empty weight on the overall frame while still safely absorbing extreme landing shocks.
We have seen how the explosive burst power of an eagle, the total aerodynamic perfection of an albatross, and the structural resilience of a tiger are literally rewriting the mathematical rules for DARPA's synthetic flight simulators. It proves beyond a doubt that nature is the ultimate original research and development lab, and it really just leaves us with this one super provocative thought. As we continue to push the absolute boundaries of technology, what other incredibly adapted animals out there might hold the exact secrets we need for our future engineering challenges? Thanks for joining me on this explainer today. Keep asking the big questions, and always remember to look to nature for the answers.